Hello students, welcome to EPG Padasala. I am Dr. K. Gunasegaran from Center of Advanced Studies in Crystallography and Biophysics, University of Madras. Today we are going to discuss on the module Analysis of Macromolecular Structures, Ramachandran Plot. This is actually a part of the paper Biocrystallography. After completing this module, we will be able to understand protein structure classification, conformations of structural components of a protein, understanding the Ramachandran plot, validation of a protein structure using Ramachandran plot. Actually, I am very happy to be here for one reason. This Ramachandran plot, which is a very huge contribution to structural biology, crystallography and structural bioinformatics by Professor G. N. Ramachandran from University of Madras. Proteins, we all know, is composed of 20 different amino acids. Each amino acid, apart from carbon, nitrogen, hydrogen or oxygen, they have different types of chemical architecture. By the way, the 20 amino acids are different and unique. The function of each protein directly related to its structure. We have already seen a polypeptide, which is a linear chain which folded into a three-dimensional structure. By the way it attained a defined three-dimensional structure, then only it exhibits the function. That's why the structure becomes important for the function, or a particular function always demands a particular structure. To attain particular structure, proteins were synthesized using 20 different amino acids having different chemical structure and characteristics and folded into a given three-dimensional structure. The function of a protein varies with structure, which I said, and then the structure varies with the composition of amino acids and the sequence complexity. That's why sequence determines the structure and then structure determines the function. So this is called structure-activity relationship. And role of proteins in biology. The proteins are functional tools in living organisms. They play various functions. For example, structural support, defensive proteins. Some proteins are defensive, right? Some proteins are actually protecting proteins like structural proteins. And some proteins are responsible for signal transduction. Some proteins are responsible for production of energy. Some proteins are responsible for transportation along the cell walls, etc. Protein structure classifications. We already said protein is important, and then protein is a polypeptide which folds into folded conformation, which is active conformation. Now, protein structure basically it can be classified into four. One is primary structure, secondary structure, tertiary structure and quaternary structure. As you see here, primary structure is nothing but the information about the amino acid sequence. M, T, A, G, H, Y, S, S. So there is a sequence. This is the amino acid sequence of the given protein. That is primary structure. And then in the secondary structure, have a particular sequence of 8 residues or 10 residues or 12 residues, how it folds or how it has a defined conformation. So secondary structure, for example, a particular given sequence make a alpha helix or maybe a beta strand. This is secondary structure. In the tertiary structure, how the overall sequence means how all these secondary elements are folded to have a final folded conformation, which is called as tertiary structure. In the quaternary structure, sometimes a protein is not functional as monomeric, whereas it will form a multimeric structure, then it will be functional. For in this case, chaperone is shown here. 6 times the same monomer is repeated. I mean, many times it is repeated to form a ring-like structure. Only at this ring-like structure, the chaperones are functional to perform what it's supposed to do. So primary structure is the sequence, secondary structure is the alpha helix or beta strand-like structures, tertiary structure is the overall organization of the secondary structures in a 3D structure. Quaternary structure is multimeric formation of different monomers together. Now it is conformation of a protein. What is conformation? The spatial arrangement of atoms in a given molecule is called as conformation. For example, a small molecule. For example, yes, 6-membered ring. Take cyclohexane. This could be chair conformation, board conformation, skew conformation, sofa conformation. You have seen all these things in your previous classes. Now, similarly, proteins also have different types of conformations. X-ray diffraction experiment used to get the possible stable conformation of a protein which gets crystallized, because protein is a dynamic molecule. So a protein can undergo a kind of movements always. In the crystal structure, we arrest in one of the conformation. That's what we detect as the crystal structure. From the figure, one can understand that phi and psi are torsional angles about NC alpha, C alpha, C prime bonds, by which the two adjacent peptide units can be oriented. Peptide units are nothing but amide linkages, CONH groups. In the diagram, you can see a box has been drawn. This whole four molecule, these atoms lie in a plane. So peptide unit is a planar one. So there are two peptide units. For example, take the middle carbon, which is connected this side to N, that side to C double bond O. So with respect to the central carbon atom, we have two peptide units, one this side, one that side. These two are represented as planes. So these two planes can be oriented with one another with respect to the central atom. That is what actually determines the complete conformation of the molecule. So this is what's shown in this picture. Structure activity correlation. In the figure we can see a polypeptide, which is actually many peptide units, many amide units repeated along. And the peptide units are shown as a elliptical shape, because already we have seen that this is a plane and this is a plane. These two planes are connected to the central carbon atom. So the orientation of these two planar conformations about the central carbon atom is determines the conformation. There are two red lines on drawn. This is N-C alpha connection. Other red line is C alpha C connection. So there are these two bonds. These two red lines are showing bonds. They are single bonds. They are rotatable bonds. That means with respect to these rotatable bonds, these two peptide unit planes can be oriented. That's what in the next picture it is shown. There are many planes are drawn. These planes are boxes. These boxes are peptide units. And then we can see the C alpha carbon atom. The C alpha carbon atom is connected with these two planar peptide units. And then there are angles are noted here. Phi, which is the torsion angle about the NC alpha bond. Psi, which is the same way, it's the torsional angle of the bond, which is actually C alpha and C. So phi, psi, these two are the torsional angles. These two torsional angles with respect to the central atom, central C alpha carbon atom, it explains the orientation of these two planar rings, which actually defines the conformation. And then the lengthy chain of polypeptide, it is actually a polypeptide, it's not yet protein. When this completely linear polypeptide, when it is folded as exists in the nature, then only we call it as protein. So protein is a polypeptide. The only difference is this polypeptide is not a linear chain. It has been folded to have a defined three-dimensional structure by non-covalent interactions. Now each protein has its own structure. That's why that exhibit its own function. So structure always determines the function. That's what we call it as structure activity correlation, or structure function correlation, or structure activity relationship. We said proteins, it has to have its own three-dimensional structure to exhibit function. And then that means if you want to explain the function, we should understand the structure. That's why we go for crystallography, because crystallography is the ultimate tool to get the three-dimensional structure of a molecule, be it a small, medium or macromolecule. There are other techniques, but crystallography is the ultimate tool to arrive, particularly in the case of protein structures. So we use crystallography and then we get the model. Means we have determined the three-dimensional structure. Now there are some questions. These are the following questions frequently put forward to a crystallographer. Is the crystallographic model is justified? Since the enzymes or proteins perform functions by dynamic motions of atoms, does crystallography gives us any insight into these motions? Are some parts of the molecule more flexible than others? Right. So these are the questions put forward to a crystallographer when we get the initial structure. And are major movements of structural elements essential to molecular action? Can we see these movements in the crystal structure? These are the things. when these all the questions, I mean the last three questions can be answered from thermal parameter analysis, because in crystallography we don't not only find the position of atoms, but we also give the value, I mean what extent it vibrates around its central point, means to what extent the atom is actually dynamic, thermal motion. That's what we call it as thermal parameters. So from the thermal parameter analysis we can answer the dynamic nature of the atoms, which portion is flexible, which portion is not flexible, all these things. But the first question, I mean how to validate the structure, how the model can be justified, that always needs a fundamental validation, right? Since in proteins the peptide chains folded to arrive at a 3D structure, the possible orientation of peptide units with respect to one another becomes important factor, and obviously Ramachandran plot becomes inevitable for such validation. The first question, which is how can we justify the model? Is the model is correct? To answer this question, we have to analyze the structure to Ramachandran plot. As residue by residue we have to analyze, the 5 psi combinations have to be verified to make it the validity of the model. And then how Ramachandran plot validate the protein conformation? Here in this picture you can see it's a small peptide unit, dipeptide unit. There is a middle carbon atom. This atom has 2 peptide units, one this side and one that side, means 2 amide units. These 2 amide units are planar, which has been shown in the rectangles. So these 2 planes can rotate with respect to one another with the respect to the central atom. That is what actually determining the overall folding, because along the polypeptide chain, these peptide units are going to be oriented with one another with respect to the central carbon atom. In the picture you could see phi and psi. These 2 are the torsion angles, and around these torsion angles, phi represents to what extent the NC bond can be twisted or can be rotated, because NC is a single bond, CC also a single bond. When there is a single bond, obviously rotation is possible. So these 2 peptide units relative orientation with one another can be explained with these 2 torsion angles. So phi is NC alpha and psi is alpha C prime. And then probably, I don't know, but just I'll take a minute. This is the torsion angle. If there are 4 atoms are connected like this, 1, 2, 3 and 4. So these are the 4 atoms, right? So if you want to see if it is a single bond, around this single bond this rotation is possible, means like this. There are 4 atoms, these atoms are rotatable about this middle bond. So we have to calculate this called as torsional angle. I'll just take a moment. And then here let's see, the 3 atoms like 1, 2, 3. These 3 atoms can be fit in a plane, and then 1, 2, 3. These 3 atoms can fit in a plane. That's what it is. 4 atoms like 1, 2, 3, 4. Now about this middle bond, this can be rotated, means the angle between this plane and this plane, this is a torsional angle. This is what the dihedral angle between these 2 planes. So this represents, means this torsional angle represent to what extent these groups are twisted or rotated. That's why it is called as torsional angle. That's why this phi and this psi, these two torsional angles represents the relative orientation of these 2 peptide units. This is a greatest contribution by Professor Ramachandran and of course from University of Madras. And then in this case we could see the possibilities like, and then it's theoretically they calculated. Now Ramachandran plot is originally completely theoretical, but it validates each and every experimental model, whatever the method you use to get the crystal structure. In this picture you can see 3 strategies. Now the first strategy, phi torsion angle is set as 0 and psi torsion angle is varied. In another, psi is set to 0 and phi is varied. And then in the middle, this phi and psi combination will talk about only the backbone, whereas side chains also important. The backbone side chain clash has also been verified by Ramachandran. As a result of these 3 strategies, they developed a map which is called as Ramachandran plot, which explains which are all the phi psi which are all these two torsion angle combination values are energetically allowed, sterically allowed, energetically disallowed, sterically disallowed. Here we could see the three set. First strategy I told you is phi set as 0 and psi we vary. There are three pictures you can see here. In the first one, we set psi is equal to near 0. For example, phi 0, psi 0. Here in this picture you can see O1, H1, sorry, H2 clash. Means 1 represents from the first amino acid, 2 represents from the second amino acid, means adjacent amino acid. So, when both are phi and psi are 0, we could get O1 and H2 clash. In this case, when phi is near 180, O clash is happening. But anyway, all these clashes are sterically increasing the energy. So this kind of possibilities, phi-psi combination cannot exist for steric reasons, energy reasons. Here we see a diagram. This is a graphical representation. In x-axis we have psi of phi angles, and in the y-axis we have psi angles. Here it varies from minus 180 to 180 in both the directions, x as well as y. In the x-axis phi, so which represents the phi angle, and then psi represents the psi angle. In the picture you can see some areas are shaded, means some phi-psi combinations are disallowed, or even we don't need to say disallowed, at least we can explain these are all the area where steric clashes are more, means atoms will collide with each other. So this type of phi-psi combinations are energetically unfavorable. In both the diagrams, the shadowed regions are showing what type of clashes are possible. For example, in the first diagram you can see O1, O2 clash. So these are the regions where O1 and then O2 gets collide with each other. So these areas are not allowed. Means these phi-psi combinations are energetically unfavorable. The same way in the middle region you can see O1, H2 clash. Means in this region, in this phi-psi combination, O and H, they collide or they clash, which actually energetically unfavorable. In the second diagram, the shaded region explains O1, C2 clash. So mainly the shaded areas are not allowed because of steric clashes. They are unfavorable because of the energy reasons. Here there is another situation where we set psi is equal to 0 and then we vary phi. There are two here. One, when the phi is near 0, we see O1 H2 clash. When phi is near 180, we expect N1 H2 clash. So when it is both are 0, similar to phi psi the other situation, here also we get OH clash, and when phi is 180, near 180, you could see in the diagram very clearly the nitrogen of the next residue is interacting with the amide hydrogen of the previous residue. So this clash is happening. In the middle, any value of phi, psi as 0, and then you go on change the phi, we can expect this kind of HH clash. So all these clashes means when phi is near 0 and phi is near 180, and then there are some values in between also found out with the clashes. So this kind of orientation also helped Ramachandran to calculate the area where unfavorable interactions. So we can very simply avoid, or it is not sterically allowed. So we can calculate the energy of these regions, and then we come to the conclusion that these are the regions which are not allowed for energy reasons because of steric clashes. Combining all these three, by combining these results, there are three figures are shown in this diagram completely, like HH clash, OH clash, or NH clash. All these clashes are designed are shown in a shadowed area. So in the third diagram, the overall picture is completely seen. All these shaded region are disallowed or unfavorable because of steric clashes. Because of the steric clashes, because of the energy reasons, these regions cannot be assumed by a amino acid sequence. That is a conclusion of this Ramachandran plot based on the backbone interaction. By doing this, keep phi and then rotate psi, or keep psi and then rotate phi. These experiments, these theoretical calculations led us to have this particular beautiful plot which is called as Ramachandran plot. So this is the overall complete picture of Ramachandran plot or complete phi psi plot. So this plot represents, these are the areas. The region where we could see the shades is not allowed because of the steric clashes. And in the spots, the black spots are explaining the position or the combination of phi and psi by which an amino acid take its own conformation in the given polypeptide. So in the figure you can see there are white regions which are favorable regions. So whenever there is a spot in this region, means such a phi psi combinations assumes or provide a particular conformation, an helix, a strand, or similar to that, to a given sequence. In the next diagram you can see some shaded, some areas are called anti-parallel beta sheet, some are parallel beta sheet, some are collagen triple helix. So this is the diagram where phi varies from minus 180 to plus 180 along the x-axis and psi minus 180 to plus 180 along the y-axis. In this, for example, for the left-handed alpha helix, here both are positive, means both phi and psi are positive values, that to about 60. Then you can have a left-handed alpha helix. That's what it means. And then all these blue regions are allowed region, all the other shaded regions are not allowed regions. In the blue regions, anti-parallel beta sheets, parallel beta sheets, collagen triple helix, right-handed twist sheets, and even right-handed helix, alpha helix. These are all available, these are all possible conformations by this phi psi combinations. And then that's the reason for a structure, any structure determined by any mean, there is a big polypeptide obviously. So it contains phi and psi values. The phi and psi values of the given sequence, given structure, it should fall within the Ramachandran plot, whatever the method you solve the structure of a protein. So by combining these two, this called, if there are some points, you can see there are some points which are in the shaded region. These shaded region are disallowed, we already said. Still, there are some reasons if some spots are available there. For example, glycine and proline, it can occupy these places because glycine has no side chain. So it's highly flexible because of its hydrogen. So the number of clashes are very less. So glycine can be anywhere within this Ramachandran plot. So for glycine there is no region is called unfavorable or disallowed region. For proline, proline is a cyclic amino acid. Because of this also it has a special orientation, so that can have these places in the disallowed region. Other than glycine and proline, whatever the amino acid, in whatever the structure, in whatever the way you solve the structure, the phi psi combination should fall within this allowed regions. The combinations lying in this region, for example, in the shaded region is a disallowed region. When there are some spots or there are some combinations which falls in this region, they are called as outliers. Unique features of Ramachandran plot in structure analysis. Actually, Ramachandran plot clearly depicts how well the phi and psi angles are clustering, and that reveals other oddities that may be the result of errors made during refinement. So Ramachandran map validates the structure and then it guides the structure refinement. Ramachandran plot is one of the simplest and most sensitive means for assessing the quality of a protein model in the absence of experimental data, since phi and psi angles are not usually restrained during X-ray refinement as opposed to bond length, bond angle, and for instance. Crystallographic software packages and map fitting programs usually contain a routine for computing phi and psi for each residue from the current coordinate list, as well as for generating the Ramachandran diagram and plotting a symbol or residue number at the phi and psi. So that's what every software, obviously it has to be incorporated. So every software has its own Ramachandran plot module by where we can see real-time phi psi combination for each and every amino acid by putting the cursor on the amino acid. So phi psi combination is useful for determining the amino acid's role in secondary structure. Also useful to verify the crystal structure or NMR structure. Further, during molecular dynamics calculations, for example, molecular dynamics becomes more and more important nowadays because once you know the protein structure, you can simulate it to explain its function. But during the simulation also, you cannot violate phi and psi. That is always important. So even during molecular dynamics simulation, phi psi map is always guiding us to give restraining refinement. So we keep on. We should not go beyond the allowed regions. If so, during molecular simulation dynamics also, these trajectories can be verified or set using phi psi plots only. It is highly useful to set constraints and helps for the defining energy functions. We said outliers. Outliers are the phi psi combinations which falls in the disallowed region or unfavorable region. Why? Because these regions, these phi psi combinations will show the possibility the clashes, so energetically unfavorable. But still, this number of outliers are a very important criteria in protein structure determination. See here, the protein data bank. This is a PDB, you can get this from the PDB website also. Here, an important criteria for a protein structure is number of outliers should be very minimum. Means it should a valid structure, a good structure should contains mostly all the spots within the allowed region. Means number of outliers should be very minimum. Here there are two examples are shown from the PDB websites here itself. The topper one shows a poor structure, the bottom one shows the good structure. In the third line you could see Ramachandran outliers. For the poor structure, 14.5% are the Ramachandran outliers, and whereas in the good structure it is 0%. Means no residue found in the outlier. When number of outliers in the disallowed regions is minimum, then that tells the structure is more valid. The must structure is more accurate. We already said outliers are not good. So number of outliers should be very minimum for a good structure. If it is possible, we should have a 0 outliers except glycine and proline, because we already said glycine is highly flexible and then proline is a cyclic amino acid. There are some special stereochemical considerations, so they don't give rise to much clashes, so they are allowed to be in anywhere. But other than these two residues, all the residues should fall within this allowed phi psi combination range. Okay, here Ramachandran plot is not only used to validate the structure, it is actually more useful when we are refining a crystal structure. We all know we get the X-ray diffraction data from the protein crystal. From the crystal, we solve the structure using different types of phasing methods which we are not discussing here. And once we get the structure, it is called rough model at the beginning, then we have to refine it. When we say refine it, means we get all the residues, means all the amino acids well within the electron density, so that sometimes we may need to rotate the amino acids along phi psi angle, so we have to move this to the density, because in a highly resolved structure, the electron density will be completely covering the residues, means the residue will be completely fit into the electron density. At that condition, number of outliers will be very minimum. So in that case, Ramachandran plot mostly used nowadays to monitor the progress of the structure refinement. For example, in the above, the first figure shows the above image depicts initial refining stage. where R factor is 49%. And the next slide, next picture, R is 18%, which means refinement is almost over. Now, when the refinement is almost over, you could see the clustered of all these 5 combinations within the allowed region. Whereas in the first one is the initial stage, so there are many outliers. That tells the first thing is wrong, that has been even we can see from the R factor also. So Ramachandran plot is highly useful nowadays to monitor the progress of the structure refinement. We already said Ramachandran plot is for the validation, as well as it is highly useful nowadays in the monitoring the structure refinement. For example, here the first one shows it's called a ProCheck module, which is a component of PDB sum for validating the protein structure which has been deposited in the PDB, protein data bank. And then here is the ProCheck output. This is actually explains the Ramachandran plot. Now you could see how many residues are well within the allowed region, and then how many spots are in the disallowed region. That clearly explains. And then we could see within this red shaded area, all the spots are crowded. That means the crystal structure is highly validated. It's a very good, highly refined structure. So that is the validation of this validation report using ProCheck. In the next slide, you could see in this is actually a WinCoot snapshot picture. WinCoot is a software where we do the modeling of the crystal structures when we do the crystal structure refinement from X-ray diffraction data. And then you could see densities, right? So we build up the electron density, and then within the density we grow the sequence. We place the sequence, and then we try to fit the sequence well within the electron density. That's what a proper crystal structure is supposed to be. So when the complete atoms of an amino acid well within the electron density, if it is highly resolved data, structure, that will be very clearly seen. So here also we could see there is a small window opens for the Ramachandran plot. So here it is actually a dynamic plot, means when you put a cursor on a residue and then click it, now that will immediately show the Ramachandran plot of that residue and every residue. But once you rotate the residue, or when you move the residue, we could see at the real time the spot is moving along this Ramachandran plot also, which is very helpful. By rotating an amino acid using the software tool, we can immediately monitor the movement of this 5 combination, and then we can there itself we can decide are we going in the right direction or wrong direction. Because at the end of the day, in a right structure, in a completely refined high resolved structure, number of outliers should be very minimum. In this case, for example, it has been shown there, if 80% structure is correct, only 6 outliers in this case, right? So the number of outliers is a good mark to tell about the validity of the structure, as well as it is highly useful to monitor real-time structure refinement protocols. That's why this type of modules are Ramachandran plot. Without Ramachandran plot, there is no software. All the softwares, be it structure determination software, structure refinement softwares, or even molecular dynamics software, everywhere Ramachandran plot has been taken as the checkpoint. So to monitor the progress, or to validate the conformation. We already seen every protein structure, be it a crystal structure or NMR structure, whatever it is, every 5 should be within the allowed region. And then we also said if some points, some combinations falls away, this is called outliers. And we also said glycine, proline, these two are exception. Okay. Now, when an outlier, it is warning some discrepancy. When there is an outlier, it tells, oh, there is something wrong with the structure. But sometimes there could be a reason for such anomaly. In fact, such disagreement may occur as a response to a stimuli. For example, a input signal from the ligand binding, or approach of the substrate, or the receptor that may tell us a clue. So as a consequence, such conformational changes could contribute to change in enzyme activity or in the affinity of protein ligand, protein-protein, or protein-DNA interactions. Outliers, they are not allowed. If there is an unavoidable outlier, then we have to look into keen, and then we may find something new from that out of it. That's the idea. Let us now summarize what we have learned in this module. Since structure determines the function of a protein, establishing a correct model is very important. Ramachandran plot is highly useful to validate and experimentally determine structure. The plot explains the possible orientation, which means energetically allowed, of two successive peptide units with relevance to the central C-alpha carbon atom. Apart from this, the plot is highly useful to monitor the progress of successful structure refinement. Hence, in all the structure refinement softwares, the plot is incorporated to see the real-time movement of 5' combinations upon movement in the residues. Hence, in all the crystal structures softwares, the plot is incorporated to see the real-time movement of 5' combination. The unavoidable outliers in a plot may contribute for the function by ligand binding or by exhibiting a molecular switch kind of arrangement. So we have to be very careful about the outliers, and then we don't need to ignore. Then we have to find out if there is an outlier, what is the meaning behind this. This is the end of the module. Thank you so much.